Hi. In this program, we're going to take a look at buffer calculations. Let's first review a little bit about buffers. Here we have a titration curve between a weak acid and a strong base. The region that I've highlighted here in red indicates what we call the buffer region. In that region, we have both present a weak acid and its conjugate base. So I'm going to represent that by the following equation. Here we have our weak acid dissociating into its conjugate salt, the weak base, and an H+ ion. This has an equilibrium constant, which can be expressed the following way. Ka is equal to the concentration of the hydrogen ion times its conjugate base divided by the concentration of the acid. I'm going to rearrange this equation now so I get the H+ ion by itself, and I get the following. I now want to apply the P operator. Now we've seen that before in things like pH and POH, pKa. So when I do that, P, remember, is the negative log. So the negative log of the H+ concentration now equals the negative log of Ka plus the negative log of the weak acid over its conjugate base. These negative logs apply to certain definitions. For instance, the negative log of H+ becomes the pH, the negative log of Ka becomes the pKa, and now I'm going to switch the sign here and make it plus the log by inverting the fraction of the conjugate base over Ha. This is the expression for a buffer solution of a weak acid and its conjugate base. There is a corresponding equation for a weak base and its conjugate acid. Both of these are worth applying to memory, especially when you're dealing with buffer questions. Remember that these apply only to weak acids, not strong ones. Let's look at a couple of questions that will involve the use of these equations. First of all, let's select the appropriate acid to use to create a buffer whose pH is about 5. Let's bring up the relevant equation that we've just developed. Remember, to have an effective buffer, we want it to resist both attack from acids and bases. That means the concentration of our conjugate base and our weak acid should be about the same. So that would mean we'd have the log of 1, and that's 0. So from this equation we can see that if our designed pH is 5, we want a pKa as close to 5 as possible. So that would mean we'd probably select the acetic acid. Let's look at a further question. Using this chosen combination that we have in A part, determine the salt concentration required to use with a 0.1 molar solution of the acid to prepare a buffer whose pH is 5. Let's begin by taking the equation that we have above and substituting in the values we know. Our target pH is 5, pKa is 4.75 from the table, plus the log of our conjugate base over 0.1, the concentration of our acid. We now can move the 4.75 over to the other side, and we get 0.25. To remove the log, we raise both sides to the power of 10, so we get 10 to the 0.25 equals the concentration of our conjugate base over 0.1. And solving then for the concentration of our base, we get 0.18 moles per decimeter cubed. I hope you found that useful. Comments are always welcome, and thanks for watching.